a few words about the logo and the name. EngAstros means Enhanced Modeling and Astroseismology of δ-Scuti stars in Closed Binary Systems. And as you can see here, there are two stars. The left one is the pulsating star, while the right one is a companion star, which is a normal star, let's say. They are surrounded by the rose lobes, and since the program is going to study eclipsing systems, you can see that these rose lobes are also surrounded by a light curve of an eclipsing binary. However, the name EngAstros is the paraphrase of the name HelAS, which was a giant in Greek mythology and was connected to the earthquakes. However, this word hides the ancient words en plus chime, which means lie inside, and the word astro, which means star, in order to say that we're going to study the oscillations of the stellar interior. However, there is another view of this logo, and you can see it as a face that leads to an image of a crazy scientist performing research. Okay, now with the humor part, I'm going to introduce you now the δ-Scuti stars. They are pulsating stars of AF spectral classes. They pulsate with periods between 20 minutes and 8 hours. They exhibit radial and non-radial oscillation mode, driven by the kappa mechanism. And as you can see in the right part, they lie inside the classical instability strip. EngAstros combines two different topics of astrophysics. From one hand, we have the pulsating stars, and with astroseismology, we can learn a lot about the physics of stellar oscillations. On the other hand, we have binary systems, and especially when we talk about the eclipsing ones, we are able to calculate the physical parameters and the evolutionary stages of the components. Therefore, combining this information, we get extraordinary knowledge for this specific evolutionary era. This histogram shows the demographics of δ-Scuti stars members of binary systems, and according to their rose geometry and their type of variability. So far, we know approximately 340 such systems. However, only for 70 of them, their absolute parameters have been calculated. This diagram shows the correlation between the orbital and pulsational periods of these objects. You can see that there are two groups, one for shorter orbital period values and the other for the longer ones. Our team, before a few years, established a threshold. Beyond that, these quantities seem uncorrelated. So if we zoom in now to the first group, the one with the shorter orbital period values, we see a more clear picture of correlation. And this correlation is slightly different when we talk about the semi-detached systems or detached systems. These diagrams include the δ-Scuti stars members of binary systems, and we can see clearly that they are mostly main sequence stars, in contrast with the single δ-Scuti stars that, as you can see, they lie above the terminal age main sequence. So we concluded that the companion star accelerates the initiation of the pulsations. Another useful diagram is the correlation between the surface gravity and the pulsational period of these stars. And as you can see, as the stars are distant from each other, this correlation tends to be the same with that of the single δ-Scuti stars. So the proximity of the components plays a crucial role for the preservation of the pulsations. This diagram includes in the MR diagram on the horizontal plane and the frequency, the pulsation frequency on the vertical axis. And we can see clearly that the younger the star, the faster the pulsations. So far, we have published two versions of the catalog. Of course, each version had a different sample. the first one in 2012 and the second one 2017. Hopefully, the following years, we are going to update this catalog and the properties of this system. However, for those that are interested, there is also the online version of this catalog in my personal webpage, when you can see updated frequently. EngAstros has open questions and goals, of course. Some of the questions are, for example, how exactly the companion affects the pulsations of the δ-Scuti star, which are the differences between single and binary member δ-Scuti stars, what is the pulsation history of these stars in terms of initiation and evolution, and finally, the €1 million question, which AF stars become pulsators. In order to try to answer some of these questions, we will obtain a large sample collection, and using the property of these stars being members of binary systems, we will calculate the physical parameters and the evolutionary stages of as many as possible targets. Subsequently, we will make their pulsation models, and finally, we will categorize them, and we will try to find the properties of each group, and the more important one, to find possible links between these groups. For the implementation of the project, we will need a lot of targets in order to be analyzed photometrically and spectroscopically. The type of analysis you can see in the right side, it will be 4 different ones, and I will talk about them later. Initially, we will use the 153 known eclipsing systems for pulsation analysis and spectroscopic analysis as well. However, new cases from space data and from ground-based observations are anticipated to be revealed. At this point, I would like to bring to your attention the revolution for astroseismology that space data brought. You see in this diagram 2 light curves. The above light curve was observed by the TESS mission, while the lower one from a ground-based observatory. And as you can clearly see, there is tremendous difference of the photometric accuracy that reflects to 1 to 2 up to 3 orders of magnitude less noise in the frequencies calculation. So using space data, we get high detailed pulsation models. As already mentioned, we will perform also photometric and spectroscopic analysis. For the photometric data, we will use mostly data from the Kepler and K2 missions, as well as from the TESS mission. And we will download the data from their online archives. However, for targets of specific interest, we will use the 1.23 meter telescope of Crioneri Observatory, and for bright systems, the 40 centimeter telescope of the University of Athens. However, for southern targets, we will use small telescope from our Australian colleagues. For spectroscopy, we plan to use the 2.3 meter Aristarchos telescope and the 2.3 meter telescope of the Australian National University. A few words now about the analysis. For systems that exhibit orbital period modulations, we will apply the eclipsing time variation analysis in order to find the most possible orbital modulating mechanism. For the eclipsing systems, we will have for which we will have their light curves. We will perform binary modeling in order to find the light curve residuals, on which we will apply Fourier analysis in order to derive the pulsational model, as well as to identify their oscillation modes. Of course, this will be combined with spectroscopy. If we are lucky, we will get in the majority of the systems radial velocities for both components in order to calculate the mass ratio, and the spectral classification for, again, if we are lucky, for both components. We will combine all this information in order to derive the absolute parameters of both components, and then using the binary star evolutionary code and or the MESA code, we will able to produce the evolutionary model of the system. So using as many as possible targets from the space data in their majority, we will combine our analysis results with that already known from the literature, and our goal is to create the most complete and coherent catalog about these systems. However, the new catalog will include the subgroups of these systems and hopefully the links between them. At this point, I would like to highlight that EngAstros has been submitted as a research proposal to HFRI and currently is under review. In case of success of this project, proposal, we will upgrade the Aristarchus transient spectrometer in order to measure radial velocities. 2 PhD students will be employed. And finally, the group, which is led by Greek scientists, will become highly competitive at international level in the topic of astroseismology. Thank you very much for your attention.
Thank you for the talk. Let me enable people to be able to speak. So if you have questions, either raise your hand or put them in the chat and I'll try to monitor. There is one by Grigoris. Go ahead, Grigoris.
Hi, Alexis. Nice work. I would like to ask you, with respect to the evolution, if you have an idea. I mean, why these stars are born with such kind of pulsations, and what would be the future path for this? I mean, are these pulsations going to be more intense when they evolve or drop out? I don't know.
Okay, as we know from the classical stellar evolution, as the star gets elder, the pulsation amplitude and the frequencies are going down. So this is more what is expected also for these stars. We don't know exactly why the pulsations are initiated earlier than they would if the stars were single stars. So it has to be connected with the companion star and possible mass transfer rates or other proximity phenomena. So we're not sure why they initiate earlier, but we are sure, as I showed you already in the 3-dimensional diagram, that the pulsations are getting lower as the time passes.
Okay, next question by Manoj.
Hello, this was a very nice talk, and the project is very interesting. So I have a similar question with Grigoris, which goes on probably, as you said, mass transfer or tidal interaction should play a role on why you have pulsation earlier in the evolution. And my question was whether you want to go towards the direction of trying to take this into account in your astroseismological model, because especially if you use like detailed models, you can take into account maybe the tidal interaction of how does it change the structure of the pulsating one, and then try to see how differently it will pulsate or why it pulsates when it shouldn't. Is this the idea or the direction? Is it something feasible, or is it something, or are the two components of the astroseismology and understanding what is the binary kind of independent and cannot really talk to each other?
Yes, there are many cases. So far, there have been discovered 3 cases of tidally oblique pulsators. And we see that in these stars, there is a strong interaction with their non-pulsating components. So the pulsations differs from side to side of the pulsating stars. So this can be observed, but you need very, very close binary systems, I would say, with a few days of period. However, regarding your comment about the mass transfer, we need long-term data in order to see if there are differences in the amplitudes or the frequencies themselves. So far, in order to do this, you need rapid mass transfer binaries. And to my knowledge, there are only a few of them for which we have determined that indeed the mass transfer is the key, plays the key role for changing the amplitude and the frequencies in a time range of approximately 20-25 years. So we need with the space data, we have a long coverage, approximately 5 to 10 years. So there might be some systems in there which are of this kind.
Thank you.
I have a question. So these pulsations, they break the symmetry, the spherical symmetry of the star, right? And so I'm wondering, would you expect to measure polarization of the light of the star?
I didn't catch the second part.
Would you expect the light of the star to have some fractional polarization, either circular or linear?
Okay, I don't know about this. I haven't thought before about this, but I haven't seen any paper talking about polarizations. Regarding the symmetry, you expect symmetry in the pulsations only for the detached systems and those that have long orbital period values. As I said before to the other question, there have been at least 3 systems we see that there is no symmetry in the pulsations. The side of the pulsating star that facing its component shows different pulsation behavior than the other side. So I expect that as you move outwards the pulsating star, you get symmetric pulsations. But regarding your comment about polarizations, I don't know.
Okay.
Sorry about that.
No worries. Thanks. So next up, we'll have Mr. Antoniades Karnavas. Hopefully you can share your screen. If I can find you in the participant list. I don't seem to see the speaker in the list. We are running a bit early, 2 minutes, so maybe we can wait a couple minutes to see if the speaker shows up. Grigori, you have your hand raised.
Yes, in the meantime, if we can fill the time, can I ask Alexis something more?
Sure, go ahead.
Alexia,
yes, I can hear you.
Do you have any idea if there is magnetism in these stars?
There are some stars that, you mean the pulsating stars or
Yes.
the components?
Either the pulsating or both of them that could interact in order to make these changes in the...
Yes, of course, but the majority, you don't expect magnetism in these stars. However, there is a specific category of δ-Scuti stars, or not δ-Scuti stars, pulsating stars they are similar to δ-Scuti stars that have magnetic fields. However, in the binaries I showed you, there are their components, I mean the non-pulsating stars. In many cases, there is strong indication of magnetism in terms of spots or flares, nothing more, okay? but they are mostly main sequence stars or giant stars. They are not neutron stars or some exotic objects.
Okay, good, thanks.
You're welcome.